Hi, this video is about the asymptotic growth of functions. So in the first part of the video, we're going to be looking at different functions and how they behave, specifically in terms of their growth rate. In the next part of the video, we'll be formalizing the notion of big O, theta, and big omega. And finally, I'll talk a little bit about the master theorem, which allows us to solve a very specific type of recurrence very easily. So let's get started with just thinking about the different kinds of functions and how they behave. Keep this in mind out here. The context for looking at asymptotic growth of functions is the running time of algorithms. So we are not really interested in the specific value of a function. If I give it an input, what is the value of the output? We're not interested in that. What we're interested in is, as my input increases, how is my function changing? Of course, we are going to be looking potentially at functions that are monotonically increasing. So they always increase, they don't decrease. But that's not really a requirement. We are also going to be restricting ourselves to integer inputs just because it's easier to think about. Doesn't really impact anything that I'm going to say. Okay, so to start out, let's think of the simplest function that we can have, and that is the constant function. So the constant function basically doesn't change at all even if the input changes. So your function could be fn is equal to 10 or 100 or any number that you can think of. Doesn't really matter. If my input n goes from 5 to 6 or 500 to 501, the output is just the same. So in that sense, I could actually club all constant functions into just one constant function because their behavior as the input changes is exactly the same. As I've said before, and I will say continuously throughout this video, the specific value doesn't matter. What matters is how the input is changing. The next function is actually pretty straightforward, and that's going to be a linear function. And as you can see, this is basically the identity function. It just spits out whatever you give in. Again, what we're interested in is in the growth of the function. So this actually gives us a very interesting insight into thinking about how the function changes as my input changes. So take a specific example of n going from 5 to 6. My output goes from 5 to 6, which is an increase of 1 unit. If my input goes from 500 to 501, again an increase of 1 unit, the output still changes just by 1 unit. So the change in the output is the same irrespective of where the input is, whether it's at 5 or at 500, the growth of the function is the same. And if you think about a function that grows a lot faster, let's say fn is equal to 2n, right? We find something interesting. So if my input changes from 5 to 6, my output goes from 10 to 12, which is an increase of 2. If it changes from 500 to 501, my output changes from 1000 to 1002, which is again a difference of 2. So for the same change in the input, my output is changing by the same amount. So in that sense, in terms of the behavior of how the function, the growth of the function is changing, I claim that all of these linear functions, whether it's fn is equal to n or 2n or 3n or some 2.5n or some variety in between, basically behave the same. Also interesting to note is, suppose I have a function that is a combination of a linear function and a constant function. What's going to happen if I have 2n minus 1? I could draw this. It's basically going to be the same as the 2n, except it's shifted down by 1. So if you think about the impact that that's going to have, if I move my function up or down, the specific value at an n is going to change. But we don't care about the specific value at a particular n. What we care about is how the function changes. And the constant has no effect on that. So voila, we come to the conclusion that not only fn is equal to n or 2n or 3n, but also if it's a generic linear function, fn is equal to 2n plus 56, I'm still going to get the same behavior as fn is equal to n. So far we've looked at two families of functions. One is the constant function. The other is the family of all linear functions. And we group them as a family because effectively as n changes, the change in the output is the behavior of the change in the output is the same, in that it is constant whether n is at 5 or at 500. Let's look at an example where this does not happen, and a very good example of that is the quadratic function. So if I have fn is equal to n squared, I'm going to have a function, if you remember from high school, that looks like a parabola, right? And out here, we have something very interesting going on that is different from what was happening with linear functions. So in the standard example that we take, let's say n goes from 5 to 6, a difference of 1, and 501, 500 to 501, again a difference of 1. So my input is changing by 1. But in the first case, my output goes from 25 to 36, which is a change of 11. When the input goes from 500 to 501, the change in the output is 1001, right? So there's a huge difference in the output for the same difference in the input. So as my n increases, not only does f of n increase, but the change in f of n also increases. And for fans of calculus, this is kind of obvious, right? Because the change that we're talking about is basically the derivative at that point, and that's going to increase as you go up. That's not important. What's important is you understand the behavior out here. As my input increases, my output changes a lot faster than it did before. For a linear function, the change in the output was constant. Out here, the change is increasing, right? Okay, so that is for fn is equal to n squared. What happens if, like last time, I say n squared plus 2? Nothing much. All that happens is I take this curve, it shifts up, or if it's negative, it shifts down. The point is that while the value of the function might change, I don't care about that. What I care about is the rate at which that function is changing. And that behavior doesn't depend on the constant that I'm adding. So add a constant, doesn't matter, behavior is the same as n squared. What about if I have twice n squared or 3 times n squared? Again, it's the same thing. The rate of change we are multiplying by a constant. So whatever behavior I'm getting for n squared at n equal to 5 or 500, I'm going to get the same kind of behavior for 3n squared, right? Last thing, suppose I have a combination of a linear function and a quadratic function. So for example, if I have n squared plus n. So here's the interesting thing. So the change in my output, I can compose as the change because of n squared term and the change because of the linear term. And again, we know that the change in n squared increases as n increases. So as n keeps increasing, the effect of n squared starts dominating because the linear term is just increasing by the same amount irrespective of the value of n. So in that sense, I can take the generic quadratic equation ax squared plus bx plus c, and I can say that any equation, any function of this form basically behaves the same as just n squared. So this is the third family that we are looking at. So the first is the constant function, the second is a linear, and the third is a quadratic. You can imagine, we can keep going, right? We can do cubic, quintic, and cubic, quartic, quintic, and so on. But in each case, as you can imagine, the dominant factor is going to be the highest power of n, right? And these are all polynomial functions. So for polynomial functions, if I have a power of 0, that's a constant term, I'm going to get essentially a straight line, a horizontal line, and the output does not depend on the input at all. The function does not change. If I have a linear function, the change is constant irrespective of the value of n. But as I go to higher powers, the quadratic and cubic terms, the output changes, the rate of the output changing is much greater at higher n than it is at lower n. So if I think about the rate of change of the function, higher order polynomial functions change more than lower order polynomial functions, okay? So just keep that in mind. And now let's switch gears and look at something that is not quadratic, not a polynomial function. Let's start looking at an exponential function. And I'm going to take, so in general, an exponential function is c raised to k. I'm going to take something like 2 raised to k, just as an example. And I could just plot these values, right? I could say for n going from 0, 1 to 3, what is 2 raised to n? And for comparison, I've also listed out the values of n squared. And as you can see out here, we start out with 2 raised to n being greater than n squared, and then it becomes equal, and then it actually becomes less than n squared, right? So we might say, okay, as we increase the value of n, maybe beyond 3, 2 raised to n is smaller than n squared. Maybe, maybe not. Let's take a few more points, right? So for 4, I have it equal, but then for 5, I have 25 versus 32. And as it turns out, after this point, we always have 2 raised to n greater than n squared. And the reason for that is 2 raised to n grows faster at a faster rate as n increases than n squared does. Here's an example. If I take n equal to 10, I can have n squared will be 100 and 2 raised to n is going to be 1024. It's 10 times greater, right? So if I were to plot this, I'd probably get, something like, that's my n squared term, starts from 0. And my 2 raised to n starts from 1. It dips below these two and then it goes up. It grows exponentially, and hence the term, like if you want to say something is growing very fast, we say it's growing exponentially. So that's the idea out here. So we can also state, similar to what we did for polynomial functions, that all exponential functions belong to the same family in that their behavior is similar. What do we mean by that? It doesn't matter if I take 3 raised to n or 4 raised to n or 10 raised to n, the exponential behavior is still the same, right? And why that is left as an exercise to the reader. It's pretty straightforward mathematics. Okay, one last large function is n factorial. I'm going to let you guys try to plot it, but also think about how you would analytically, or how you would analyze the behavior of n factorial versus, let's say, 2 raised to n. And it's fairly easy to think about because your 2 raised to n is basically 2 into 2 into 2 n times, whereas n factorial is n into n minus 1 into n minus 2 into 1, right? And we can do a pairwise comparison and see that, of course, n factorial is going to grow faster than 2 raised to n. Right? That's a pretty straightforward way of doing things. Okay, so what's our total catalog right now? We've got polynomial functions, and is the constant function part of that or not, or is it on its own? Who knows? Then we've got, in the polynomial functions, we've got linear, quadratic, cubic, and so on. Then we've got the exponential functions, and we've got factorials. All of these are in order of, each one is growing faster than the previous one. Let's think about something that grows slower than a linear function, but still is faster than a constant function. So an easy way of thinking about that is, 2 raised to n grows faster than a linear function. So what about the inverse of 2 raised to n? How would that behave? What's the inverse of an exponential? It's the log function. So I could go ahead and calculate the value of log n for different values of n. And being a good programmer, I'm also very lazy. So instead of taking n being 1, 2, 3, 4, 5, I'll just take powers of 2. So 1, 2, 4, 8, 16, 32, simply because log n is straightforward. And as you can see, as n increases, log n grows pretty slowly. And in fact, if I were to plot, this is my linear function, and this would be my logarithmic function, right? It grows a lot slower. So again, we're not interested in the actual value of the function, where out here it is a lot slower. But as n increases, the growth of log n itself slows down. And that rate is a lot smaller than the rate of growth of a linear function, which, if you remember, was a constant, right? I could do this for a few other functions as well. So what about n log n? How does that fit in our catalog of functions? What about square root of n? So what I'd recommend is put down different values of n, plug in the values, plot the graphs, think about it. If you're so inclined, you could take the derivatives and play around with them, or like we did with the exponential versus factorial, just do a pairwise comparison of the points and see what we get, right? So that's homework for you guys. The other thing that we can think about also is something like n raised to n, right? And that is again, what would you compare it with? You could compare it with n squared, you could compare it with n raised to k, or you could compare it with n factorial. And you can do like we did before, one is you could just actually calculate the values and plot them. The other is you could do write down the first few terms or write down the nth term and do a pairwise comparison with some of the others. Okay, so I'm going to stop out here. I want to end with a recommendation for these two websites, GeoGebra and Desmos. They allow you to graph simple functions on the same, and it works through your browser. It's really fantastic. You can play around with all kinds of functions, look at them, understand when one function has a value less than the other. What happens if I add a constant? What happens if I do n squared plus n, or n cubed plus n squared plus n plus a constant? So play around with that, get a feel for how functions vary. Okay, why is this important? So now let me link this into algorithms. So these functions represent the running time of the algorithm, and the input to the function n is not the value of the input to the algorithm, it is the size of the input to the algorithm. So the question that we're trying to answer is, as the input to the algorithm increases, how does my running time change? So for a small running time, I'll have some, for a small input, I'll have some running time. As the size of my input, let's say, doubles or it grows 10 times, does my running time also become 10 times, in which case it's a linear function, or does it become 100 times, in which case it's a quadratic function, or God forbid, is it 2 raised to k, in which case it completely explodes, right? So that's the context in what we are doing. In the next part, we're going to be looking at the specific ways of, or I shouldn't say specific. In the next part, we're going to be looking at a mathematically precise way of defining how the rate of growth of one function compares to another function. Thank you.